Okay, let's start with the class of today. Today we'll continue to see instability in the stars. I'll show you a little something more about the thin shell instability, so to be a little more clear how it works. Then we'll see the dynamical instability, passing through a little model that is a classical model, the Piston model, that compare the star or a sphere of gas, like a gas inside a piston, and we'll see how is working the stability for this moment. It's quite simple, but managed to show several characteristics of the several kind of stability or instability. Last time we saw the thin shell instability. Tonight, it happens when you have a small shell around the core, obviously, where you can have a production of nuclear energy, and so there is something deposit a lot of energy, cause an expansion, and we see that this expansion not working as the secular stability, that the expansion cool the gas but increase the gas. Here show from another point of view, show maybe it managed to be a little clearer, taking obviously no, yeah. The classical approximation of the generalization of the equation state, the pressure is proportional to a power of density and a power of temperature. Remembering what was the gravothermal heat capacity, and heat capacity connected with also the gravity. That is what is a characteristic in stars that essentially when I compress it increase when not I compress, when the gas compress itself, the temperature arises. The formula of the gravothermal heat capacity is this one, the heat capacity at a constant pressure, and you see depend on the adiabatic gradient and the exponent. And for the thin shell, it's below is depend on the ratio among the radius and the size, the thickness of the shell. If the thickness is really small respect to the radius, we have that an increase of the shell, of the thickness, causes similar effect to a reduction of the density. We have an expansion, so the density decrease a little. But since the increase in the thickness and the cause in proportional relative increase of the radius that is smaller than usual because of the thickness is small, we can consider that the expansion doesn't cause a great movement of the superior layer, so the pressure is more or less the same, at least relatively to the top and the value of the pressure. So it doesn't manage to cause a great increase in the pressure. And if you take this one and derivative to have the relation among the relative variation. We have this one, and considering that for a thin shell, the pressure, this value, relative variation is almost zero, we have that are just connected the variation in density and temperature. So for an increase, when delta X is bigger, that means that this decrease will change, and we have that if we have decrease of the density, this is negative, with the minus is positive. That means that an expansion increases the temperature. As you saw above, but maybe here is definitely a little more clear what happened. The gas expand, but since the thin shell is small, it can expand, reduce its density without changing too much the pressure to the superior level. So it expands, but the pressure from side doesn't change, so stay the same. That causes that if you have maintain everything, not lose energy, the an expansion causes an increase of temperature. Increase of temperature, as before, cause an increase in the nuclear production that cause an ulterior another expansion, and so on up to a certain point where the gas expand sufficiently to actually to have cooling of the gas. This happens essentially always when you have a burning shell where the energy production by nuclear reaction are really dependent on temperature. So you have for small temperature, you have a great increase in the production of the energy. This is quite typical, in fact, for the helium shell. You will see that this typical scenario of the, as I say, the asymptotic Julian branch that have this classical helium shell instability that cause some pulsation and several mixing in the outer layer. As said, we are going to see now dynamic stability. So the instability that happens in the star, oops, it's not perfect. When we have the several layers, they are moving, expanding, or contracting, and see how this can be stable or unstable. A classical model is a piston model. They approximate everything as the gas we are considering expanding as a gas inside a piston. The superior level, the outer layer is are the piston with a certain mass m. The mass of the gas below is considered to be really smaller than mass of the piston. This simplify the calculation also for the potential energy, because essentially we have to balance the pressure from of the gas mass m with the gravitational force from the superior level of mass capital M. And we saw here the gas, the piston. The piston is the upper layer. Ts, this is an S, is the temperature of the system outside. In the case when we have a leak of calor, of heat from the gas inside the piston with the outside environment. We have the classical formulation. Gravitational force is minus G by M. G is the gravitational acceleration. Consider positive in this case. Just not be confused with the sign. Take the everything positive, so we put the minus in the formula. The force due to the pressure, that is simply the pressure of the gas inside, multiplied by the area of the piston, among the piston and the gas. The volume of the gas is H, the height from the flow of the piston, of the distance among the piston and the floor of the chamber. The mass of the gas here is can be connected with its density multiplied by the volume, or the density multiplied by the surface of the piston multiplied by the height, distance from the piston from the floor. The potential energy is simply, as I said, the mass of the piston is definitely greater than the mass of the gas, so just consider the potential energy of the piston is a really simplified piston, because essentially, as you saw, technically it has no thickness. It's just really heavy plate among the gas, and the internal energy of the system is just due to the temperature of the gas, its mass. The classical coefficient multiplied by temperature and the mass. Calculating the motion equation, you have the mass of the piston, essentially, because so the mass definitely greater than the mass of the gas by an acceleration, by the second derivative in the time on height, is equal to the sum of the two forces that are this one, quite similar, and if you have an equilibrium, we have the pressure multiplied by the surface is equal acceleration of gravity multiplied by the mass, as quite similar to the equilibrium, industrial equilibrium we saw before. We can calculate the Dirac theorem for this model, that is in this way. Potential in this one. You can, using this case, you see definitely pressure G prime is the pressure divided by the surface, so pressure divided by the volume, and the volume can be changed in M divided by density. So we have the pressure divided by density can be bring to a relation with internal energy. In the case where the acceleration of gravity doesn't depend on the height, as a classical approximation on the surface of the Earth, because the acceleration we have a small variation, so it doesn't change a lot. In ideal gas, we have the classical. No, not the classical, the opposite of the classical, but because we have the variation of the potential energy is equal to 2/3 to the variation of internal energy. So to decrease the I of the piston, I have to decrease the temperature of the gas. That is obvious. If you have a gas inside, they are not losing energy, classically said, to decrease the volume. P, pressure by volume, is proportional to the temperature. To decrease the volume, I have to decrease the temperature. Usually, we always thought about that we compress a gas, so the volume decrease and the temperature increase. Yes, but we are doing a work on the gas. Here, there is not something from outside the model that's doing a work. In the stars, there is no one compressing stars. It's doing everything by itself, so you cannot consider something from outside and doing a job, and only the work done internally. So we have this difference from a star. This can be changed if you just consider that the celestial gravity depends on the height. Using ideal gas, put in this way, that this gradient of the gravity is the logarithmic gradient among acceleration gravity and the height. So if you deliver by the height the potential energy, we have this relation that we know that this one, so we have also this one. The adiabatic coefficient doesn't depend on the height, so it's just this one. So at the end, we have a relation for the variation of the internal energy by the height. And we, okay, if you consider that this gradient is 0, we are coming back here. As before, the internal energy is proportional with the proportional positive constant with the height. So to decrease the internal energy, we have to decrease the height. It's here, obviously, but it's consistent. On the other side, if you consider that the gradient is less than 1 minus 1, in this case, then we have that this value here is negative. It's not more. Before was positive, was just 1. Now it's negative. So going back to the similar to the for the stars, the internal energy, the relative effect to the height is less than 0. That means if you the gas decrease in volume, so decrease the H, the internal energy increase. That is exactly what we want as in the start. Just to have consideration, if you this gradient is minus alpha, then the acceleration gravity is proportional to the high to the minus alpha. That essentially the case classical Newton, this alpha is 2, because the high is essentially the distance from the center, and so it actually is correct because minus 2 is less than minus 1. So essentially what happened? That in stars, a mass shell lose weight when they increase. The star expand, the shell expand, and since it's farther away from the center, its weight, not this mass, decrease. Don't make confusion among weight, that is a force, and mass, that is a property of the matter. The weight is the multiplication among the mass, property of the matter, and the acceleration of gravity that is due to the gravity, gravitational effect. Now, this consider the part depending on the heat. Variation of heat can be seen as production of energy or variation in the flux due to opacity, or a loss of heat by differential in temperature with the sun. This key here is just a constant that gives us a relation. If not when insulated, we can lose heat from outside. That is connected, as usual, variation in temperature and variation in height and work by the system. To consider stability, what usually is done, classical, you consider a relative variation of our property. Divide is zero starting value. This is a classical, essentially all the physics branch. The variation is the variation, the new value from certain time less the initial value, divide the initial value, and we consider that this relative variation can be expressed as a function of just the properties and a function of just of the temperature of the time. X is not the position, it's just a general variable, but connected with the properties. And then we consider that the function depend on the time is just an exponential. With the frequency here, it is a complex value and not a real value, to a more general. This maybe is something that we already saw in quantics or other parts. Is usually to simplify, is used in this way to separate, for example, the part depending on the space and the time, or for variation in time, or separating two variables, because it's reasonably to suppose that the function is not connected, the two are to separate. So we can have the three variable, essentially the height of the piston, the pressure inside the gas, the temperature of the gas, the varying in this way with zero temperature, 1 plus the value depend on the properties, and then something they change with the time. With all of these value, their absolute value really smaller than 1, so what is called small variation, small oscillation, we just shift a little from the position and see what happened to the system. That's essentially what we want to know about stability. As I said, the first class of stability, if the it's a stability really stable, like a ball in a valley, you have the with a small variation the ball will fall back again inside. In the other case, where we have instead an equilibrium, but it's stable, just with a small variation, the ball will fall down, or we can have the third solution. I think this is called the neutral equilibrium. The ball on the horizontal plane, that if you change, the ball stay move a little in one direction, so it's not dissipated, but doesn't go away quickly from the original position. Doing some simple solution, again, it goes back to a case where the gravity, acceleration of gravity doesn't change with the height. So this gradient is 0. Acceleration is only constant. I know is not the physics of our situation, but it's nice to see characteristic of the stability, considering a adiabatic process, so there is not a loss of heat from the border of the piston. The temperature is inside staying the same, if not moving, nothing. We have so the classical I by omega is more or less plus minus E by this adiabatic frequency that depend on the characteristic of the system, and H0 is the initial high, and the adiabatic coefficient. You can rewrite this equation this way. This also something familiar. The mass we can have because J divided by H, it's the similar to the several form you see also for the free fall and expansion, something like that. This is the case of periodic oscillation. So a stable equilibrium, you give a little E, and the piston just going up and down, up and down, up and down continuously with small variation, small oscillation as classic. If it's not adiabatic, but is the loss of energy by outside, considering there is no nuclear production of nuclear energy inside, just a piston. We have that is what is called here the solution in this way, as before, adiabatic, but there is in time more that is negative. You see, coefficient adiabatic coefficient -1 usually is greater than 1, and everything is positive here. This is the we can redefine this as a time, from the time that give the characteristic time of the due to the loss, and essentially it's minus. That means that exponential goes down the oscillation. It is what's called in fact a vibration stable with damped oscillation. The system started to oscillate and smaller and smaller and smaller. Classical, if you have a ball in a valley, the friction start to oscillate and then losing energy goes down again. It is essentially vibration stable because the vibration doesn't cause to go far and far away from the equilibrium position, but to go nearer and nearer to the equilibrium position. You can see a third solution if the evolution is really small, so evolution is low, so slow that the static equilibrium is maintained constantly. And in this case, the E omega is just a negative value. Essentially, we have what is so before the circular stability. If you have we change a little, the system moves back to the equilibrium position with just exponential movement. Go asymptotically again toward the position of equilibrium. In the case that we consider more physics for us situation, so the gravity depends on the position, and considering that this gradient is less than -1, so something similar to the star, I define now G0 as the gravity at the equilibrium, with the pressure on the equilibrium, as before, not considering production of energy, no opacity, and no adiabatic. Anyway, just to have a change in the gravity with the height, with the distance, we have that the previous adiabatic frequency that was classical stability by periodic oscillation. Now the value is not more perfectly, it's not sure that is actually positive, but can be negative. Here inside the square root, when the adiabatic coefficient is greater than this value, the frequency is real, so we have an oscillation. Now, but if the adiabatic coefficient is less than the minus of the gradient, so is less than 1 in this case, we have a solution that causes an enhanced oscillation, because here this is negative. So the root square is or negative number is plus minus the result multiplied by E. So we have a plus minus or something real. So it's not more this value is real now in a more complex number. So we have in the case we have as I say so before, the circular decrease exponentially, but can increase exponentially. So we can have the dynamical stability or instability. As also we saw that one kind of stability, dynamical, vibrational, or secular. And dynamical is this one, way, vibrational we have with loss by energy, we what causes the expansion, the contraction, lose energy in another form, so it's weaker and weaker. For circular, that just the variation are dumped internally, goes away, are not connecting with each other, so one kind can exist and the other not, and cause an influence in the evolution of the system, etc. What is changed, and that is the system is dynamically unstable, the other are less important because usually the dynamical instability can be really quick and bring quickly everything outside the equilibrium. So it's what is more important, what is stronger in effect. Now let's see what happened to the stars, numerical stability. Considering spherical symmetry, this means that we have just a radial perturbation, compression and expansion. Not other. Can be something different, but now we just consider this kind. As usual, we have the classical situation, the hydrostatic equilibrium and the continuity equation. In general, this is what rule the stability, because this came from equilibrium, dynamic equilibrium. Now we can change, we can see what happens if I change a little the system. As so before, we apply a little modification, we can compression. We pass from the variable R density and pressure in the same prime that is after the compression, and we can express the new radius value as the radius multiplied by 1 minus epsilon, with epsilon really smaller. So these are classical homology relation, because also the each ratio inside the stars, the ratio because the final and the initial value are constant. For density, for pressure, each one is a relation, but it's constant among. This is the reason why we introduced before the homology, explained, because it's used a lot. And since epsilon is small, just remember Taylor expansion. So 1 plus minus a small variation to the end can be rewritten as 1 plus minus n by variation. So the density is can be expressed in this way from the continuity. If you change here R with this value, we obtain that we have all the equation for the density, the initial density, divided simply by 1 minus epsilon everything to the third power. That is more or less using the approximation to this value. So then, as we have the value of the radius is proportional to the initial value, also density, the new value is proportional to the initial value by a function of the epsilon. To simplify, we consider just adiabatic. We are not losing it. Beta is almost 1, but essentially the pressure is just given by the gas. This permits to simplify a little. So the gradient among pressure and density is the adiabatic coefficient. So the pressure of the gas can be represented in this way. So density is in this way. We put this value. We get this solution. Small variation again in this way. From the hydrostatic equation, we have now the new value for the pressure to have hydrostatic equilibrium must be this one. This one is the pressure that is now in the gas. This is the pressure that is needed for the equilibrium. It's different. And you can see that they are different because this one it just depends on the pressure initial and the position. This one depends, the pressure of the gas depends obviously on the adiabatic coefficient. The pressure of the gas depends on his equation state. Changing equation state, it changes how we vary the pressure. That means that after the contraction, the two pressure are not more equal, but can be are different. So we have a situation if the pressure of the gas is less than the pressure of the divided by the equilibrium, we are considering the contraction. So contracting, the gravitational effect start to be greater. So if the pressure is smaller, the contraction will continue. We have instability. If the pressure of the gas, new pressure of the gas, is greater than new pressure needed by the equilibrium, we have stability. So in this situation, rewriting the two value. Taking away the pressure, one is taken away. We have the epsilon here, but we say that this epsilon is positive because we have contraction, and the contraction is already considered by the minus here. So epsilon is greater, so we adjust for stability that the adiabatic coefficient must be greater than 4/3. And this here explains why in the several classes we looked to the how the adiabatic coefficient vary in several situations with the pressure of the radiation, changing the relation actually among the pressure of the gas and total pressure with the ionization and so on. Because now we saw the value of the adiabatic coefficient is enter also in the stability, dynamical instability. We saw before that this value can be also connected with the other kind of instability. Essentially with the so the thermal instability, there are relation. Consider relation in the equation of state that are connected to the adiabatic coefficient. Must have to be greater than 4/3. And we saw that when system have a adiabatic coefficient of 4/3, it can be problematic. You have to notice that the 4/3, the third came from the gravity law, and the third from the continuity. Actually, the fourth came also the continuity because it came here for potentially from the equation the static equilibrium here, but this include the term from the gravity and the continuity because we change from gravity respect to the radius to the mass. So it's this situation, the continuity is just okay, something geometrical. The value, the critical value, is something intrinsic of the system. It's not pure something apart, but is given by how it's working the gravity gravitational effect inside the star. If we have a different relation for gravitational effect, that value will be different. So this is embedded in the gravitational law that we need stability with the adiabatic coefficient. This is mechanical statistics. That is gravitational law. It's nice to see this relation among something different. So if you have a adiabatic coefficient greater than 1.3333 per third, for all the radius, we have a dynamical star system independently stable. If the adiabatic coefficient is equal to 4/3 for all the radius, we have neutrally stable, as you say when it is the plane. The ball on the horizontal plane that doesn't change. It is because in every contraction the system found itself again in a static equilibrium, not doesn't change. But if the adiabatic coefficient is less than 1/3, then we have to check if this integral on all the stars is negative, then we have a global dynamic instability. Because it's not important that in some part there is this violation from the stability. It's needed that is enough to cause instability, serious instability of the stars. But consider it everywhere. So you can see that depends both on the value of this difference and also the value, the ratio among the pressure and the density. It is actually, remember, connected to the internal energy. So when there is a high internal energy of the part, is more important, is different than where is a smaller value. Just to consider, as I said, connected to the internal energy, but considering the several situation, adiabatic process, or simply gas, P divided by density is proportional to the density. Remember, usually coefficient adiabatic coefficient is greater than 1, so this is positive. So if you have higher density, it is higher. Or consider this one. If you have an higher temperature, this value is higher. That means that in the core, this value is definitely bigger than the envelope. That means that a dynamically unstable large core can lead to instability of the star. Why? The dynamic instability of the envelope can be just lead to a periodic oscillation. That is what we saw in the periodic stars. We have an instability of just in the outer layer, not periodic. It's not a problem. It doesn't cause random destruction of the stars, but stay just there. Or you can see sometimes the dynamic instability of the envelope can lead some loss, mass loss, but not disrupt on the stars, just disrupt on the envelope. Now, a little bottle need to drink a little. Okay, now let's see some physical connection with situation. Again, relativistic generated gas. Here, the dramatic constant tend to the fourth third. Tend is definitely not easily that is everywhere to the fourth third. Remember that perfect degeneracy doesn't exist. Mathematically can exist, because you can go also to the absolute zero, but in physics, in the nature, you cannot have a perfect degenerate as a core completely degeneration. Degeneracy can be perfect everywhere. In the core, there is maybe in the center, it's degeneracy is really high, almost complete, but through the core just decrease, we have can be 90% of degeneracy. Is not perfect. That is also permitted to the stars, as we saw, to survive some case with the like the alien flesh, because the equation state is not always perfectly not dependent on temperature. It was just independent of temperature. You will just the temperature increase with the reaction, and there is complete runaway. There is always a small dependence on the temperature, so the increase the pressure that causes expansion, then permit to the core to rearrange. Usually we have a gradient of degeneracy inside. Relative in motor relativistic is in the center, outside decrease, and the upper part is a mix of degenerate gas and not degenerate gas. Also, remember, usually it's the electron are degenerate gas, the ions are not, because if you just consider hydrogen, it is one proton. The proton has 2,000 times the mass of the electron, so it's definitely more complicated. You need an extreme case to have degeneracy for them, like it happened in neutron stars, degeneracy also with the neutrons, but the density there is absolutely bigger, because usually the degeneracy of the electron starts with the density of 10 to the 6 grams per cubic centimeter, while the neutron stars, if I remember, it's like 10 to the 18, something completely on the other level. So the gas is always two parts, the electron that is generated gas, and the ions that are in ideal gas. Since there are exchange of energy among them, if you hit one, it's a change, so a change in pressure, a change in expansion density. But anyway, in relativistic generated gas, as the relativity generacy increase, a bigger portion of the core is enabled unstable to the contraction. And when the core, the mass of the core is more or less of the mass of the Chandrasekhar, the dynamic pressure is not more enough, and the contraction increases the density. This will increase the degeneracy, so we have this situation. Essentially, we have a neutrally stable for the Chandrasekhar. The problem is that in this situation you can have other instability, the thermal with a nuclear reaction that cause other problems. So it's we go in approximation there, but it is not more. It's a sum on stability. Radiation pressure, as you see previously, we have the derivative coefficient depend on beta, and you can see in the 7D notes, not the image 7D, but the note with the mark with the 7D, where the variation, relative variation pressure depend on the adiabatic coefficient gamma 1. This is the generic. When the three adiabatic coefficients are equal, then they are equal to the adiabatic coefficient, the adiabatic coefficient. Gamma 1 is this gradient is this value. You can see the change with the pressure of the gas is dominant. We have the gamma 1 is a third. That in this case it is equal to the adiabatic coefficient, the value of the adiabatic coefficient. If the beta goes to 0, so is the gas of the pressure of the gas is less dominant. Is what is dominant radiation pressure. The gamma 1 is going to the value of third. In this case, not similar to the adiabatic coefficient because the event goes to infinity. This is because the gamma is just equal to the specific heat at pressure constant divided the specific heat at volume constant. But this value goes to infinity because the pressure doesn't depend on the volume. So for B equals 0, we have relativistic gas, and because essentially we have seen that essentially all the pressures determined by the radiation. And the visual theorem, remember us that for relativistic gas, we have the internal energy is equal to the opposite of the potential energy. That means the total energy is 0. So we have this system is unbound. As before, we are running to the value of third, so it's not essentially real instability. It's neutrally stable, but is there, and you need a little to disrupt the system. You have essentially instability for expansion, and this is a mass loss. This is typical situation when dominant radiation present in stars with the high mass stars or stars that really big radius, like the red giant, red supergiant, and so on. High mass will be the giant, blue giant. And where you can have essentially this mass loss due to the radiation pressure to the wind. They are pushing away the external layer of the gas. Then we have a family of situation on ionization and company. Essentially is not only ionization, everything that we have in atom plus a photon, this can lead to the production of more material. Instead, in the case of ionization, you have the simple that at the beginning you have the ionization of hydrogen. The molecular mass is 1, and with the density of 1, number of particles, essentially. Here is change start to be 1/2 because you have 2 particles. But essentially, everywhere when considering the relation among the density and the numerical density and the molecular mass, the density is constant. In situation, if you are not an expansion or something like that, this is constant. The mass, unit mass, atomic unit mass is constant by definition. So we can have the numerical mass and the molecular mass if one change to the other. You saw that both enter, and we have essentially ionization. All the process they are changing our numerical mass and numerical density of the gas. Can usually increase or the opposite process will decrease. Okay. Considering, for example, ionization, X is the degree of ionization, the ratio among the, taking into consideration hydrogen, since it's the main atom present, main element, the number of hydrogen ionized ones, obviously, respect to the total number of hydrogen present. If you have ionization, the degree of ionization increase and the number of particles increase, because this can happen by with photons or collision. Actually, we passed from 1 particle to 2 particles, and we saw before. The recombination is the opposite. We have the degree of ionization decrease, obviously, and the number of particles decrease. We pass from 2 particles to 1 particle. We saw previously this equation. There are this value here, and a constant depends on several values. And depending on the temperature, the pressure of the gas, and this depends on the potential ionization potential. we can see that if you increase the degree of ionization, this part increase is essentially put 0 if here you see 0. If you process to little less than 1, this causing this just it's a really rapid increase in this way. If you have a compression, that means that the density increase, the pressure increase. If you increase this one, this value should decrease. If this decrease, this decrease. So we with the compression, with the increase of the pressure, we have the decrease of the degree of ionization, and we have less particle combination with enhanced. So with the compression, the combination is enhanced. If you have an expansion, the pressure decreases because as we saw before, in expansion, the outer layer are losing weight, so are causing less pressure on the layer under them. Is decrease the density. If the pressure decrease, this increase, so this increase the degree of ionization. We have an increase in ionization and increase of the particle, and the ionization is favorable with an expansion. This is also something that is important in the study of stellar atmosphere, because the ionization, the degree of ionization that is connected with the depth of a line in the spectra. It's connecting this way with the pressure of the gas, which is the pressure on the electron, because it's what is more connected. And this is also a way to use the line to understand the pressure of the electron, and so the gravity, and so the radius, and distinguish giant from the dwarf stars. Remember, just anticipation, the stars on the main sequence are called dwarf. Even if it's something like this big, like Sirius is not really small, or star of 20, 30 solar mass that is quite huge, but it's called a dwarf. The dwarf are stars on the main sequence. Don't make confusion with the white dwarf that is different. So what you get that the number of the particle are in proportional to the inverse to the density. So if the number is constant, we have a compression acceleration. We will not change in the variation. The compression causes the volume pass from the value of V to the V prime, that is less compression. Just remember the equation of state. So the pressure, new pressure on the value, you can calculate this way, and you see that is less than 1. you have compression, the pressure increase. Aspect before, and this permit certain reaction. If you consider that the number of particles depend on the degree of ionization, then again we have to consider that the compression and the value decrease, and as I said before, with the compression, the combination is enhanced, so also the number of particles decrease, is less on the other. Doing the calculation, the new value is you have this situation, and that this is less than 1, so we have the old value multiplied by less than 1, so the pressure increase less. That means that this relation in new situation, the adiabatic coefficient essentially in the presence of ionization is less on the adiabatic coefficient since ionization. That means also you can understand directly here that if the pressure increases less, there is a higher probability of instability, because this is the increase of the pressure that guarantees the stability. Anyway, we saw previously, or we said in the 7 notes 7, and the adiabatic coefficient in fact depends on at this value. 5 plus A is a constant, variable constant. I assume that depends on several parameters like potential, ionization potential, and so on. Just simplify in this way. If 3 plus they are similar, x by 1 minus x, you can see easily change from 0 and 1 third, 1 divided 4, 1/4, and for x is 1 and 0, the extreme value, this is 0. So in the middle, we have you see easily, this is a parabola. So we have 2 roots, the minimum have to be in the middle. The minimum is for this value. So when this things is 1/4, and at the same value 0, this goes away 5/3. It makes sense. If you have complete ionization, we cannot have a lot of variation. So the adiabatic is 5/3 as usually, or we have no ionization. Also in this case, the variation are quite small. If you consider just hydrogen, you can see the adiabatic coefficient with the half ionization. The gas is half ionized, half not. We have the adiabatic coefficient 1.21, that definitely is smaller than for third, the 1.33. Actually, you can see that the range is quite big among where the adiabatic coefficient is less than for third. So it is the same value in the middle, but essentially, if you are going away from complete ionization or not ionization, the medical coefficient is less. And this causes several types of stability. Usually, this is the main stability that is caused for the pulsation. Pulsating stars, the main process is the ionization, dual ionization of helium, actually, not hydrogen, mainly from the presence of the duration ionization of helium, and so this cause. But as I said before, this is instability, not just ionization, all the family that cause this change in the numerical density, to increase or decrease the number of particles present. So we have also the photon disintegration, like the ion is hit by a gamma ray and is disrupt from one nucleus of iron in, like, I remember, 14, 14 particles, 14 essentially alpha particle, or the pair production, where is essentially the opposite. There is also an atom, in this case just the catalysator. It's not that the atom is active, but the photon needs an atom nearby to produce, to conserve momentum and energy. And there is the production of a pair that so increase the number of particles. The pair are also annihilated with themselves, but if we have enough high energetic photons, we always have a certain amount of pair present, so this will increase the situation. It's like a ionization, producing more particles. So sample energy essentially are all situations where some of the energy goes to increase the number of the particles instead of increasing the pressure. You are storing energy there, then it goes back like the pulsation. Yes, okay, stability because of this pulsation. And it's quite typical if you consider the time of the hydrostatic equilibrium, quite stable. So there's instability, but it's periodic, so maintain more or less similar. We have the period should be actually here is minus. So if you at higher density, we are shorter period. If you are lower density, we are longer period. It is something that we saw. That star will, like sun, can have a little pulsation over a short period, actually a little bigger than the sun. You see that the instability straight that pass involved the star. But for example, red giant have a really long period. They are 18 days. Or if you are going to the Mira, they are red supergiant. A period also of several years, 1,000 days. Or you see the instability trip, they are going with the white dwarf, they are really compact, they are really dense. There, the pulsation present in the white dwarf are on the order of 4 seconds, are really, and it also makes sense if you consider something a bar of iron and you are hitting it, you see that it vibrates really quickly. If you hit something less dense, can maybe a balloon with the water, it start to oscillate really slow. If you had a balloon, air balloon, just air, really less dense, it go in heat, the oscillation are really small and not so easy to notice because are really slow. This is also appunto the pulsation happen in the envelope usually where the densities are too low, so also the density in the period is long. This is making also sense because, per esempio, in RR Lyrae, the stars present in where is in the horizontal branch, where the stars are burning the helium, essentially 99 of the star of the mass of the star is the core. It is in high density, but the pulsation are quite slow, the order of 8 hours, 6 hours, up to 1 day. And this is because, as we saw said before, it's due to the ionization in the envelope. So where the density is lower, so in lower, longer period than the global density of the star. And we stopped because we are also go more than the usual. See you next time.